Hi, my name is Sophie, and I'm a graduate student at Vanderbilt University. I'll be presenting on the predictive processing in auditory cortex without consciousness. This project is built upon previous work done by my doctoral advisor, Dr. Andre Bastos here at Vanderbilt, and his collaborators at MIT. So we know that one of the most important jobs of the brain is to make predictions. This ranges from simple things like predicting that if you reach your hand into your pocket, you'll likely find your phone, to complex predictions like how will the global pandemic situation evolve in the next few months. And many have hypothesized that this predictive process is a key aspect of our consciousness. To test this, we would have to ask the question, does the brain still make predictions when it is unconscious? And if so, what are the mechanisms of unconscious predictive processing? To answer this question, we use an experimental paradigm in which the brain will make predictions and experience prediction errors. So two types of auditory predictions were used. The first is when the first four tones are the same, we tend to predict the fifth tone to also be the same. When this prediction is violated, this creates a what we call local oddball type prediction error. The second type of prediction is created when a repeated pattern of multiple stimuli is learned. When this prediction is violated, this creates a global oddball type prediction error. This type of prediction goes beyond local sensory information and involves a more complex pattern. We collected intracranial recordings from 4 areas at different levels of the auditory processing hierarchy, namely TPT, which is a sensory auditory area, and higher order areas in the parietal and prefrontal cortex. One monkey was implanted with Utah arrays, and a second monkey was implanted with multilaminar U probes. To induce unconsciousness, the anesthetic propofol was delivered through subcutaneous vascular access ports. The auditory prediction paradigm was presented to the monkeys before, during, and after unconsciousness. From previous work, we know that propofol-induced unconsciousness creates these slow waves in the brain, which generate powerful up and down states and lock spiking activity to certain phases. These up-down neural states disrupt beta-gamma frequency activity, which has been linked to predictions and prediction errors. We hypothesize that in the unconscious state, the disrupted beta-gamma activity will no longer convey predictions and prediction errors. And we also hypothesize that global predictions will be particularly disrupted. So let's look at what we found. These are the percent change power spectra comparing local oddball and regular trials for area TPT. On the y-axis, we have frequency, and the x-axis, we have time in milliseconds after the oddball. Warmer colors indicate higher power for the prediction error. In the awake state, as we hypothesized, gamma is enhanced and beta is suppressed by local prediction errors. In the unconscious state, however, gamma and beta are both enhanced by prediction error. And surprisingly, the prediction error effect size is larger while unconscious. In addition, the prediction error response lingers for much longer in unconsciousness. And these are the percent change power spectra comparing global oddball versus regular trials for area FEF. In the awake state, beta is enhanced by global prediction error, and in the unconscious state, this effect is eliminated. We also conducted a cluster-based permutation test to identify significant changes in the power spectra for both local and global prediction errors. Frequency here is on the x-axis, and the probability of significant effects is on the y-axis. Local effects in area TPT are on the left, and global effects in higher order areas are on the right. So the upper left subplot shows that unconsciousness enhances the local prediction error effect in area TPT at all frequencies. The lower left subplot shows that during wakefulness, local predictions enhance beta in area TPT, and this effect is eliminated during unconsciousness. The upper right subplot shows that the higher order cortex responds to global prediction error with an enhanced beta, which is eliminated during unconsciousness. And the lower right subplot shows that the global prediction does not enhance power at any frequency. To conclude, as we hypothesized, local prediction errors are signaled by gamma enhancement and beta suppression in area TPT in the awake state. Contrary to our hypothesis, the local prediction error effect is enhanced during unconsciousness. Global prediction errors are processed in higher order cortex as hypothesized, but with beta enhancement. And this effect is completely eliminated during unconsciousness. So to summarize, in the awake state, predictions are generated through beta band modulation. This beta modulation is lost during unconsciousness. This generates a state in which the brain cannot form complex predictions and in which local prediction errors generate runaway excitation. Thank you all for watching, and thank you to the funding sources supporting this work.